Okay.
Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Graeme from the University of Southampton, who will talk about predictive crystallography at scale. Over to you, Graeme, please.
Thank you, Vitaly. Thanks for inviting me to speak this year. So I'm going to be talking about work we do in Southampton on crystal structure prediction of molecular organic crystals. And development of a very large database of predicted landscapes of crystals. So I thought that I'd give an introduction, so I wasn't sure of the backgrounds of everyone who'd be listening, but I thought just to sort of motivate why we are developing methods for crystal structure prediction. What we want to be able to do with these is to go from just 2D information, so bonding within a molecule and a chemical diagram like this, to predicting the three-dimensional crystal structures, all the atomic coordinates, lattice parameters, symmetry, etc. And within this arrow is quite a lot going on in terms of sampling and optimization of structures. The reason we do this, we have several applications that we look at for crystal structure prediction. A lot of work in this area is focused on pharmaceutical molecules because of prediction of polymorphism, where a molecule can adopt more than one crystal structure is very important for pharmaceuticals, for quality control and maintaining of properties, also for intellectual property. We also use these methods of crystal structure prediction in conjunction with experimental data when perhaps we have data sets from an actual material which are either incomplete or not of a sufficient quality to completely characterize a structure, say incomplete X-ray or electron diffraction. We've also worked with terahertz vibrational spectroscopy and solid-state NMR. Combining predicted structures with these can sometimes get us to a solution of resolving what that crystal structure is. And we're also looking at using these methods for trying to design or discover molecules with targeted properties. This is just a nice slide to sort of motivate why we need to understand solid-state property, not just molecular structures. These are all pictures of different polymorphs of this molecule, which has the nickname Roy. And you can see that color, crystal shape, also melting points vary a lot, depending on how the molecule is packed in its crystal structure. I show this one because it's the record holder. It has 14 known polymorphs. Also, it's nice and visual because of these different colors of polymorphs, which reflect that the packing of the molecule is influencing the electronic structure of the material. So I talked about these applications in terms of forward prediction and looking at a molecule and trying to predict what its crystal structures would be in terms of anticipating or characterizing the structures. We also do a lot now where we sort of turn this problem on its head, and rather than looking at a single molecule, what we're interested in is a property of a material or a set of properties of a material that we want. And then the question is, what molecule might give us those properties? So it's this inverse design problem. And where crystal structure prediction fits in there is that what we can do is we can test out ideas for molecules using crystal structure prediction to predict how those hypothetical molecules might pack, and from those structures predict properties so that we can sort of close this loop and try to figure out what molecules we need to go and make in the lab in order to give us a property or a set of properties that we're targeting. A little bit on the methodologies for crystal structure prediction. What we essentially do is we sample the landscape of the lattice energy of all potential crystal structures of the molecule. Here I have a very simplified form of this where I've wrapped up all of our structural variables into 2 degrees of freedom. In reality, what we have are all of our lattice dimensions, so our lengths and our angles. So there's a 6-dimensional surface there. And then we put a molecule in and we have position and orientation, so another 6 degrees of freedom. And that's just for the simplest crystal structure with one molecule in the unit cell. So that would give us a 12-dimensional energy surface, and we're typically working on higher dimensions because we might have multiple molecules in the unit cell. We might have degrees of freedom within the molecule as well. So we have orientations around bonds or stretching of bonds, that type of thing. What we need to do, or the approach we take, is to try to look for all the local minima on this energy surface. And then we want to assess those minima, each of which corresponds to a potential crystal structure for that molecule. And the assumption is that the lowest lying of these, the lowest energy minima, will be they're thermodynamically the most stable structures. We assume those will be the most likely structures that we would see if we grew crystals of this molecule in the lab. So each of those minima, again, corresponds to a distinct crystal packing. We want to enumerate all those packings, which in itself is a difficult problem. And then we want to rank them, which is also a difficult problem. The way we go about searching the energy landscape, we take the approach of doing this as broadly as possible. So we use a low discrepancy search. So all of our initial structures are as separated as possible in the initial degrees of freedom. And then we couple this just with simple local optimization. So we scatter a lot of structures across this energy surface and locally energy minimize them. And this is where most of the cost of crystal structure prediction comes in, is doing this process many, many times. We have more sophisticated approaches where, rather than just a simple local optimization, we might do something like a basin hopping, which is sort of a trajectory from that initial starting point, which was generated from a low discrepancy sequence. And that trajectory might be able to hop over low energy barriers, so we don't get trapped into sort of very shallow local minima with this kind of approach. Our software is open source. This link would take you there if you're interested in it. The other side of things, apart from the search and the initial structure generation, is how we evaluate energies. Most of what we do needs to be very quick, so we rely on interatomic force fields, so we can evaluate the interaction energies between atoms very quickly. These are not off-the-shelf force fields. They need to be better than that. And in terms of improving accuracy, what we've brought in is anisotropic atom-atom interactions, so that the way that atoms interact between molecules depends not just on distance, which is what you find in typical force fields, but also on the relative orientations of those atoms. So this can pick up directional effects of intermolecular bonding between molecules. Sometimes we need higher accuracy, and we go to things like solid state quantum mechanics, but the jump up in cost here is several orders of magnitude. So this really slows us down if we have to do that. And so something we've been working on recently is trying to shortcut that increase in cost by using machine learning methods to train approximations of solid state quantum mechanical energies of crystal structures. And I'll get towards that, get to that type of thing towards the end of my talk today. To give a little bit of an idea of the number of structures we end up generating when we look for all the structures for a given molecule. Here's an example. This molecule. Here's artemisinin. It's a natural product. Just searching in a single space group. What I'm showing here are the number of structures I've generated in this low discrepancy approach, and then energy minimized. And on the vertical axis, I'm showing the number of unique structures. So as I go along, what I'm doing is I'm finding which of those structures after energy minimization is already in my database and which of them are duplicates of something I've already found. And you see that this increases steeply initially and then starts to tail off. We want that to happen. We should generate duplicates because that's telling us that we're getting to a point where we're sampling the energy surface with enough density of points that we're finding all of our local minima. So that gives us confidence in the search. And at some point along here, we are only producing duplicates, and that tells us it's probably safe to stop. Okay. So there are no new unique structures being found. And so we say that the search has converged. And what you see is in a single space group for a small rigid molecule, that's happening at many thousands of minimizations. So if I want to look at a range of space groups, then I'm going to be needing to look at many, many thousand of energy minimizations. Okay. But what you find is the number of unique structures is only in the hundreds. We're interested in, of course, the lowest energy structures from this search. So these dashed lines I'm showing here, what they show is the lowest energy structure I've found so far in this space group. You see this actually converges much earlier, after, in this case, only a few tens of trial structures. And this is because those lowest energy basins tend to have wider basins of attraction. And so we hit those basins early on in the search, whereas some of those higher energy ones are much narrower, and those are the ones that are harder to find. If we look at the average energy of the lowest 10 structures, and now I'm interested in not just the lowest, but the lowest handful of structures, you see that converges after a few hundred. So this is just giving an idea of, depending on whether I'm really just interested in the lowest energy structure, or if I'm interested in finding all structures, how many structures I might need to sample within a particular space. A couple of applications also, just to give you an idea of how these methods get used. This is one of those pharmaceutical applications I mentioned in the first couple of slides. This was a molecule we decided to look at with John Steed up in Durham, who's a crystallographer, and Mike Probert in Newcastle. We chose this molecule because it's a drug molecule, but it had, at that time, no known pure crystal structures. It was a good test case for structure prediction. Chris Taylor, a postdoc in my group, did the crystal structure prediction with that low discrepancy sampling and calculating energies with an accurate method here, solid state density functional theory. And this is an example of a crystal structure prediction landscape. So each of the points on this landscape represents the density and the energy of a different crystal structure of that molecule. Here, the symbols and colors just correspond to different space groups, which isn't important for us now. So you can see there are a few low-lying structures, and we hope that those are the ones that we find when we do experiments. And in parallel with our calculations, John was doing some experiments in Durham. What he found is that most crystallization experiments find this one. And this is an overlay. In green and in sort of colored by element are the X-ray structure that John found and the predicted structures. You can see that geometrically, we had a very good representation of that observed structure. From a couple of experiments where he did things in an unusual crystallization setup, so rather than out of solvent, he sublimed the molecule and then sort of got it onto a cold surface, you then get a different crystal structure up here. Okay, but again, it corresponds to one of our predicted structures. But this is a pharmaceutical, and something which really scares pharmaceutical material scientists is when you see something like this. We have a prediction of what looks like a lower energy structure, and it's not being found in the lab yet. So the worry then would be that if you scaled this up and you relied on knowing what the properties were of this form 1, then you get a change in properties if suddenly you started converting to this more stable form. So we decided to do more experiments and also some more calculations. And we informed these with studies we've done over the years. This was work done by Jonas Neumann, who was a PhD student with us in Southampton, now works at the CCDC. What he did was he took lots of pairs of polymorphs, known pairs of polymorphs from the Cambridge Structural Database, and he evaluated energy differences between those polymorph pairs. And what we were interested in there was to get an idea of what is the possible range of energy differences between polymorphs. Because if we assume that the lowest energy crystal structure from our predictions will always correspond to an observable crystal, then this range of polymorph energy differences tells us how far up the landscape we expect to have to look for potential polymorphs. So it sort of tells us where to focus our efforts when we're looking at these structure prediction landscapes. What Jonas found was that over half of polymorph pairs are separated by really small energy differences, less than 2 kilojoules per mole. And almost all polymorph pairs are separated by just over 7 kilojoules per mole. So you usually just have to look for that range. If we look back at our landscape, this is where all of those 2 observed structures are sitting within about 7 kilojoules per mole. But again, this one worries us. So computationally, what we did were a few things. All of the calculations of energies that we're doing at the start of crystal structure prediction are just the static energy of the crystal structure. And we know that there are molecular and atomic vibrations in the crystals, and those will contribute to the free energy, which is what we should be looking at. Okay. So a couple things here. Ignore the pressure right now. So just look at these points. The gray dots here are those static energies of the crystal structures. And this is where this observed structure sits higher in energy than this unobserved structure. So this delta E is negative. So it's the energy difference between this unobserved and the observed structure. When you put in those vibrations, even if you don't put in any temperature, but you just look at 0-point vibrations of the atoms in the crystal structures, that order swaps. Okay. So now the one that we're seeing in the lab is actually the global minimum, still at 0 Kelvin, but it's just that we had to take into account the fact that atoms are in motion in our crystal structures. If we put temperature in, say up to room temperature, then you get to this red point here, and it's just increasing that difference. So now this observed structure is getting even more stable compared to this one over here. So that's explaining what we're seeing in the lab when they're doing those experiments in Durham. But we weren't satisfied with that. Still, this structure looks low in energy. And something we notice about it is it's higher density than the observed structure. So something we thought about trying was pressure. So we can do this computationally very easy. We apply pressure and recalculate the relative energies. And now we can do this at room temperature. So we've calculated the vibrations of atoms in our molecule, in our crystal structures. And we find that if you get to pressures of 1 gigapascal, then the order swaps back. So now this unobserved structure at high pressures is the lowest energy structure. Okay. So if we really want to get to this, then this is telling us maybe we should be doing crystallization at high pressure. This is where the Newcastle group came in. They took this crystal structure, they put it into a diamond anvil cell. They put it at, turned out you needed more than 1 gigapascal. You got up to 2 gigapascals, and then you see a transition. And it transforms to this structure here, which corresponds to the unobserved structure. So here the calculations have led us to finding the experimental conditions that you need at a previously unobserved polymorph. But now we have pretty high confidence that the main polymorphs of this molecule have been found. And that's the key thing that we wanted out of structure prediction. Another example is that idea of inverse design. This is an example from 8 years ago now, where we have a target property in mind. And what we want to do is find a molecule that gives us that. So just to quickly go through what we did in that kind of a study was we sat down with synthetic chemists. This was in Andy Cooper's group in Liverpool, and came up with some potential molecules that we thought might lead to the properties we want. The properties we wanted here were porous packings of the molecules. So packings of molecules that leave gaps. We wanted gaps that could fit methane. So we're interested in materials for methane storage, maybe for a natural gas-powered vehicle. So the hypothesis in terms of design here was to look at awkwardly shaped molecules that have strong polar groups for hydrogen bonding on their corners, with the hope that to get those hydrogen bonding interactions will sort of prevent these molecules from close packing, will leave gaps and give us porous structures. Each of those molecules, the synthetic chemists told us, would probably be weeks or months of work. So we don't want to do all of that in the lab. Instead, we do it by structure prediction. We generate all the potential crystal structures of each molecule. We energy minimize them. And now for each of those predicted crystal structures, we also calculate properties. Here, it's the amount of methane you can get in. And what I want you to look for are red points on these graphs. What those correspond to is the target range of methane deliverable capacity, those materials. And we want to be above about 150 standard temperature pressure volumes of methane per volume of material. What this lets you do is look at a landscape quickly and decide, is there anything on that landscape that could give us the property I'm after? These two landscapes at the top, they don't. Okay, so immediately we know that it's not worthwhile making those molecules, whereas this one on the bottom has some predicted structures, which do have the properties in the range that we want to. This molecule here, which corresponds to this one here, which we call T2, that's a molecule that then got made in the lab. And then after some crystallization screening, I'm circling here these structures from our predicted landscape that get found in the lab. A nice thing about having the predictions is that we can simulate powder diffraction data from each predicted structure, which lets us very quickly match things up with powder data we get from the lab. So that lets us sort of accelerate the experimental screening as well. So this structure here was the one we were interested in. So it has this red colored dot, it has the methane deliverable capacity in the range that we want. It is one of the structures that we find experimentally here. And then if we go back to the predicted properties, so here methane uptake, these triangles here are simulated data. For here, that gamma polymorph, this one here, here in black for one of the other polymorphs, this beta one, which is also porous, but less porous than this one. And then these other lines here, data points, are now experimental because we've managed to make the material, and you can see good agreement. So that means that we've gone from predicting from just molecular structure to crystal structure and properties, and we're getting this all quite accurately. So we've predicted that methane uptake for these different polymorphs fairly accurately. So that's the success story for CSP. Nice thing to point out is if you look at all the molecular crystal structures in the Cambridge Structural Database, which have the elements that we have in our molecules that we looked at in this study, that's the distribution of densities. That's the density of the structure we found in this computation-led approach. So we're finding things that were really out of distribution of normal things that we find from sort of most structures in our experimental databases. We also want to be learning now from these landscapes, because that's now going to be the theme of the rest of what I'm going to talk about. Not just the success of finding a structure which had the properties we want, but learning from the overall structure of these landscapes to try to come up with better design rules for new molecules that we're going to feed into the crystal structure prediction process. In this case, one thing we wanted to target, if we go back, is this T2 gamma polymorph here. It's a nice thing in that it's very porous. It can absorb the amount of methane that we want. But if you compare it to this red circled structure here, that's the global energy minimum, and that's a close packed structure. It's non-porous. This T2 gamma is about 50 kilojoules per mole up from that global minimum. And the reason we can get it is because it gets kinetically trapped during crystallization. There's solvent in those pores, and when we pull the solvent out, if we do it gently enough, you end up with that porous structure. But the structure is inherently metastable. Okay, and so if you start to do things with it, like putting in methane, taking it out, and cycling this process, it does eventually convert to the lower energy structures. So what we actually want for porous materials is something where you have porous materials which are the global minimum. So there's nowhere for them to go in terms of down in energy. So if we look at the landscape of this T2 molecule and all of those predicted structures, here what I'm showing is one of the contributions to the lattice energies of all of those predicted structures. And I've picked out the electrostatic contribution. Because remember, part of our design was to put hydrogen bonding groups on these molecules. And hydrogen bonding is largely an electrostatic. And what you see is that you have structures here which have weak electrostatics in red. You have structures in green, like the global energy minimum, the close packed structure, which have reasonably good electrostatic interactions for stabilizing that material. And then you have things like these porous ones, and these have this dark blue, a lot of electrostatics going on. And that's why these structures are more stable than really they should be at the density they're at, which is why these sets of structures are dropping down from the landscape in terms of where we are in density. And another way of showing that is to then look at the contributions here for that global energy minimum, close packed structure. This black bar is the overall lattice energy. In blue here is the electrostatic contribution, and we also have a reasonably good contribution from van der Waals interactions, the sort of generic interactions which stick molecules together. Whereas if we compare to this T2 gamma structure here, in that case, because hydrogen bonds have lined up actually in a nicer way than in the global minimum, the electrostatics comes down quite a bit. So you get a good extra stabilization from electrostatics, but it's at the expense of these van der Waals interactions, which are now actually destabilizing the structure. So what we learned from looking at these breakdowns of energies are, what do we need to improve? And what we decided from this was, if we could make electrostatics even stronger, then we might be able to get to a point where the low density porous structures come below the high density close packed structures on a landscape. The approach we took for that was to look at things with net charges on our components. And we were a bit inspired here from metal organic frameworks, which are a very well-used class of materials where you have organic linkers with a net negative charge bonded to net positive charge metals, and you can end up getting these porous frameworks. We decided to try to do something sort of by analogy to that. We sort of reversed it so that we would put the positive charge on the organic molecule and try to link them together with simple anions. here just some halides, chlorides, and bromides. Okay. And then the question was, by putting net charges on these molecules, are we getting the electrostatics strong enough that we're able to stabilize those potentially porous crystal structures to be global lattice energy minima? Okay. So here's one example of the combinations we tried. Here's the CSP landscape. And I'm color coding things now by porosity calculated for those structures. And what you see on this landscape is, well, it doesn't look like it's worked. Most of the low energy structures here are 0D porosity, which means there's no useful porosity in those structures. And that starred structure here is what you get when you grow this crystal in the lab of this combination of this cation and bromides. Okay. So the predictions have told us that this one wouldn't have worked. But if we look at some of the other linkers, here it's these trigonal linkers here, where we have these amines on the corners with either chlorides or bromides. Now, these are the CSP landscapes. And red are porous structures with 1D porosity, so they have channels in those structures. What you see now is that all of the low energy regions of these landscapes. So this design of stronger electrostatics into the material seems to have worked in that it stabilized porous structures. And if you look at these starred structures here, which are the global minima, and in this case, not quite the global minimum, but close to it, those are the observed structures that we get when we make those in the lab. So again, the CSP process has told us which of these combinations is going to work. We've got to that by learning from landscapes of previous studies. And so this got us to a set of useful materials. We did some more digging into these because we want to be always learning more about the next sets of structure we might go and make. In this case, again, focusing on electrostatics, we looked at how frequently does the anion get close to the cationic group on these molecules. So sort of counts of close contacts. What you find is all the low energy porous structures get there because they can really maximize the number of those close electrostatic contacts between our charged groups in these systems. Whereas the system I showed you that didn't work, what you see is that you can't get beyond about 3 contacts, whereas it seems that you need about 4 of those contacts between a chloride and an amine to get the stabilization you need to stabilize these porous structures. So again, we're learning more and more by analyzing these landscapes. You get useful properties as well. Here's something we looked at was getting iodine in and out. We can cycle this in and out and you can see it nice and visually, the material goes dark. This is useful in a sort of radioisotope capture in say a nuclear power plant. You want to capture iodine to clean things up. So these are useful materials, we think, as well, and we're exploring more properties. Okay, so now towards the big data side. So this was the title of the talk. Hopefully I've convinced you that if we analyze what's going on in terms of the structure and stability relationships on these crystal structure prediction landscapes, it improves our understanding of what makes stable crystal structures. It gives us design ideas when we want to design properties into crystal structures. And we've done this based on really small sets of structures. That initial study was only 8 or 9 molecules. The SALT study was only about 6 landscapes. So we've been working with small numbers of landscapes. And now the idea we had was, what if you could really scale this up so that you had crystal structure prediction landscapes for thousands of molecules? We think that would be really useful for really starting to understand crystallization. It's more than you have from experimental databases where you have 1 or maybe a few crystal structures per molecule. Here we have the full range of all possible crystal structures and the relative energies for every molecule that you study. So Chris Taylor, again, who did the pharmaceutical study earlier on in my talk, he led this work. And he's been working on trying to get CSP databases at really a massive scale. Okay. I'm going to show you a bit about what he's done. This was the first published bit of this work, which we published at the beginning of this year in the Faraday discussion here. And what he did was he wanted to get past 1,000 landscapes. Right? So he picked out this diverse set of small organic molecules from the crystallographic database. So we wanted all molecules that had at least 1 known crystal structure, because that's going to allow us to validate the quality of this database of structures. But you can see there's a range of things in this, from carbon dioxide up to some reasonably big organic molecules here. We looked at sort of organic functional group counts in these to make sure we were getting good diversity as well. So there's a nice range of structures or molecular structures in here. And we're at, once we've done the CSP study for all of these 1,007 molecules, we're up and above sort of 4 million crystal structures. So the way Chris did this was he looked at all the most likely space groups for organic molecules. He really wanted to push the convergence of the search, so he did 10,000 structures per space group. So we're up at just over 250,000 structures, energy minimized per molecule. Okay, and he used the force field method to energy optimize these structures. Okay. We wanted to look at the quality of the database that we've got. So one thing is going back to that assumption of, are the observed structures near the global energy minimum on the landscape? So we looked at this quantity delta E, which is looking for a match to the experimentally observed crystal structure for each particular molecule, and then how far above it is from the global energy minimum. We're expecting that if the energy model we've used for the predictions is working well, this distribution should be close to 0. Okay, where delta E is 0, and that's where our predicted structures are the global minimum. Okay, so in terms of stats from this, 1,007 molecules. Some of these were polymorphic, so there were actually 1,040 experimentally observed crystal structures that we were targeting. Most of those got found. Over 99% of those were found by the CSP process. There were a few that we now understand that didn't get hit by the CSP, and so that's allowing us to then improve our workflow for how we're doing CSP for newer molecules, but largely that's very good success. In terms of energy ranking, observed crystal structures in over 40% of cases do observe to the global energy minimum. So that's giving us validation of the energy model we've decided to apply. And if you look at, so this is a distribution of that delta E that we get, and this red line is a cumulative count here. If you look just up to 2 kilojoules per mole, then you're getting almost 3/4 of the observed crystal structures. So again, things are working very well. To give you an idea of why 2 kilojoules per mole is important, if we do a larger scale study of energy differences between polymorphs, which I mentioned earlier in the talk, if we then look at lattice vibrational energy differences between polymorphs and the contributions you get from those vibrations of your molecules, that distribution typically goes up to about 2 kilojoules per mole at room temperature. So that tells us that within the errors we have from leaving out those vibrational contributions to the free energies, all of these are essentially predicted as good as we can expect. Okay, but we still have a few out here which aren't working, but for the most part, it looks like the energy models worked well. In terms of geometries, because we don't just want well-ranked crystal structures, we want structures which faithfully reproduce what you would get if you crystallized and then did the X-ray diffraction experiment on that material. So what we use the Cambridge Structural Database structure matching to assess quality. What this does is it takes a 30-molecule cluster from the predicted crystal structure and the experimental structure and compares an RMSD of the atomic positions within that. And what we see here is that almost all cases that RMSD is below 0.4 angstrom. So that's pretty good in terms of getting the atomic coordinates right. And in a third of cases, this is below 2.2 angstrom. I point that out because if you take, again, the fact that we've ignored thermal contributions in our energy calculations, if you compare cases where you have an experimental structure which has been determined at room temperature and at low temperature, then you find that you typically get differences of up to about 0.2 angstrom. Okay, so all of these differences here, sort of below 0.2, can be explained again by the fact that we haven't included thermal contributions. Okay. And to give you an idea visually of what roughly a 0.4 angstrom RMSD difference looks like, in blue here is a predicted structure for this molecule, and in gray and red is the experimental structure, and that's got an RMSD of 0.39. That's giving you a visual idea of where most of these structures sit in terms of how well geometrically we're reproducing things. So now we think we have a nice database that we've been working on increasing the size of this, but just looking at what we've got from 1,000 molecules, we can dig into this and start to see what questions we can answer. One thing we looked at briefly, and we're looking at a bit more closely now, is if you have chiral molecules, where you can have a right-handed and left-handed version, which are non-superimposable, then if you crystallize from a solution which is a mixture of those, you have two possible outcomes. Either you crystallize where you have the right and left-handed together in a racemic crystal, or you get separation. Now, experimentally, it's well known that racemates tend to be preferred. Most chiral molecules will crystallize to a racemate, and it's rare. I think it's in less than 20% of cases do you get enantiomeric separation. And we can look at this now in our database. We looked at all of the chiral molecules, which is just over 350 of them, and we can start to look at the energy distribution of the difference between the lowest energy racemic and enantiopure crystal structure. Okay. And then we can, in those cases, we can dig into those energetics and really understand what's driving the energetic preference here for the racemic structures being lower energy than enantiopure structures, which agrees with empirically what people tend to see. One thing we notice, and it's very easy to analyze, is that most of this is density driven. Okay. When you have symmetry operators in your crystal structure, which like inversion centers or glide planes, those can aid in terms of fitting molecules together into high density structures. And those symmetry operators are only possible if you have the both handednesses of your molecule in the structure. Okay. So we can understand sort of the scale of how much of this is driven by density by having this really large set of predicted landscapes of structures. Another thing we looked at is the observed space group frequencies of organic molecules, which we know is very biased towards a handful of space groups, P1 upon C, P1 to 1 to 1. So this is the distribution of space groups that's observed experimentally. And if we look then in our CSP data sets, we can look at a few things. We can look at the distribution of the global energy minima in terms of their space groups. And what we find is that reproduces the observed space group frequency in experimental databases. So we're getting that agreement at least. We can then look at what happens if you start to include structures that are higher up the landscape. And now you start to see those distributions start to level out a bit. So you can understand then these space group distributions or biases in observed structures. It is energy driven, okay? Because if you start to go up to higher energies, then you start to see those biases start to level out. If you look at density maxima amongst our crystal structures, so not the lowest energy structure on each landscape, but the highest density structure on each landscape, then you again reproduce observed space group frequencies quite well, which is telling us that a lot of this energetic preference is probably just coming from the fact that certain space groups allow molecules to pack more closely than others, which is something which is understood for quite a long time in terms of organic macrocrystals, but it's nice to see that come out of these landscapes as well. And the final thing I wanted to talk about was coming back to the energetic cost of crystal structure prediction, and how we can use large sets of databases of crystal structures to try to shortcut that cost and bring the scale of structure prediction down even further. We're starting to look at this in terms of machine learned potentials. And the idea is that we have our crystal structure prediction landscapes. We can't afford to do high level calculations on all of those structures, but we can take a few out and we can do calculations on those with something like solid state quantum mechanics. Okay. And then we can train machine learning models. Here, we were using a committee of neural networks, and we train that to learn the energies or the relative energies of these structures. Okay. What we are actually learning in this work that we published just last year was a correction to the force field. So we're not learning the absolute lattice energies, but we're learning where there are errors in the force field when compared to density functional theory. And it turns out that with just a sort of a small number of training points, you can start to really reduce those errors in a baseline force field. Okay. It depends on how you select these training structures. If you do it randomly, you don't do so well. We applied active learning so that we could sort of learn which structures are going to improve our model most at every stage of our learning process. And that then gives you a thing that you can sort of apply and correct some quick but not very good energy models. Here we looked at this molecule resorcinol, And if you do crystal structure prediction for resorcinol with tight binding DFT, so it's sort of a cut back version of density functional theory, it doesn't do very well. You get the known polymorphs of resorcinol, but they're ranked really poorly in energy. But you can use this kind of approach of taking a few structures out, training a machine learned model to correct tight binding DFT, and then apply that correction to the whole landscape. And then what it does is it brings those observed structures down to the bottom. Okay, so we can very quickly and efficiently and sort of improve qualities of CSP landscapes. And the nice thing about that is you can do predictions quite quick with cheap methods, and this now applying this correction, it can also be done quite quickly. Now we're doing that based on a database of 1,000 molecules. So this work here was trying to correct a single landscape. Okay, so it was a model which only knew about this molecule, resorcinol. What we're interested in now is trying to make a general prediction. So we can always use this force field and we can always correct it to something which approaches DFT energies. And the reason we want to be able to do this is we want to be able to do it for any new molecule. And so we're now going to train it not just on a single CSP landscape, but on over 1,000 CSP landscapes. So what we did was we took 85% of the molecules in that study and all of the predicted crystal structures, and we put them into training. Okay, and we withheld then 15% of the molecules as a test set. Okay. Of the ones we put into training, we only took 9 structures per landscape and did our density functional theory calculations at this level of theory here. And on the left, what I'm showing you is agreement between the baseline force field here and the density functional theory accurate lattice energies here for all of those structures. Okay, and you can see we have errors of around 8 or 9 kilojoules per mole. So when I showed you really good ranking results for this database, we were relying quite heavily on cancellation of error, because we have absolute errors of 8 or 9 kilojoules per mole, but it looks like we get relative energy ranking of structures quite well. Okay, so we want to not rely on cancellation of error so much, and that means that we'll be more confident in applying the method to new or more unusual molecules. So after training on this set of now it's about 9,000, 10,000 training points, then now here's the correlation we get. We're getting errors down to about a kilojoule per mole, and that's on the crystal structures of molecules the training has seen in gray. And in blue here, it's crystal structures of molecules that are completely unseen to the training of the machine learned model. We're still getting accuracies down to about 1.5, 2 kilojoules per mole. So that's really quite good. So we have a generalized machine learned model which lets us correct force field based quick energy evaluations. If we then apply that correction to all of the crystal structures on all of our landscapes, then we can see that it improves the ranking. So these light blue bars are now after our machine learned correction. And now we've got sort of almost 20% increase in the number of perfect predictions we have, where the observed crystal structure matches up with the global energy minimum after this machine learned correction. We also get a reasonably good improvement in terms of the number of matches we find within 2 kilojoules per mole, which is that limit of where we expect to be able to be when we're still ignoring vibrational contributions to free energy. Okay. Now we still have some structures here which are not predicted well. The observed structures are above 5 kilojoules per mole from the global energy minimum, so something's still going wrong with those. And what we saw in those was those correspond to molecules where the molecule itself is a bit more flexible than most of the others. Okay, so when we applied this correction here, this delta machine learning correction to our force field, it's not correcting the structure, it's just correcting the energy of a given structure. We wanted a model now which can correct the structure in case now these molecules get distorted by being in the crystal structure. And so we trained a different machine learned potential. Now it's a message passing neural network in a similar way. But what we see is now it improves geometry. So on the left was our original prediction. On the right is an overlay of experiment and prediction after training an even better machine learned model. Okay. So we're getting now those RMSDs in terms of geometry, much lower, and in terms of energy, a lot better as well. Okay. And overall, all of those originally very poorly ranked structures really come down after we apply this machine learned model. So what we have is a framework which we're building on now, where we're doing large-scale CSP, doing machine learning to try to learn corrections to things, applying that machine learning to generate a faster rate, even more CSV landscapes, so that this thing can keep on building and building. And along the way, we're hoping that we're also learning a lot in terms of how molecules like to pack. I put that in case I have time, but I don't, so I'll skip through it to my summary. Hopefully I've showed you the crystal structure prediction methods that we're working on are useful in terms of guiding discovery materials. And that now that we're doing this at large scale, doing this for thousands of molecules, databases of millions of crystal structures labeled with energies, we're starting to label these with properties as well, that these are going to be useful for learning a lot more about how molecules crystallize, and also applying these in machine learning models, which are becoming a lot more popular within the field. So I thank people in my current research group who've been doing a lot of this work, people in bold or people whose work I've mentioned, past members who've contributed as well, and I thank the people who give us lots of computing time and funding for our research group, and thank you for listening.
Thank you, Graeme.
Okay.
Keep the slides because we might have questions.
Okay.